Okay, so far, whenever we've been finding the derivative, we've been using this notation for the derivative or gradient function of f dash x. Okay, however, there's several other notations. There's actually a lot of notations when it comes to calculus, and I think the main reason is because you had two different people who essentially invented it, so you get you get multiple sets of notations. Okay, so we're going to talk about some different notation that can be used for the derivative or the gradient function. Commonly used notations for the derivative function include, we've seen f dash of x, but you can also just write y dash. That's probably my favorite. It's the quickest to write. However, I also enjoy writing dy dx. The way you read this is dy dx. Okay, dy dx. Here's another notation where we've replaced the y by f of x. This is d dx of f of x. So you'd read it as d dx of f of x. Okay, this notation is occasionally used as well. Okay, sometimes you actually see the function put in place of f of x there. So let's have a look at the notation that Leibniz, who was one of the co-creators of calculus, used in terms of when he initially did his derivations, because he was looking at small changes of x and y on the graph. So what he did is he looked at an original point that was located at xy. We're going to call it p here, and then we're going to change the x value by a small amount. We're going to call this delta x. That's the Greek letter delta. So we're over here where x is the x value is x plus delta x. And let's say in that time y is changed by some corresponding amount delta y. Okay, so we've got x plus delta x, and the y value is y plus delta y. If you look at the gradient, which is the rise over the run of the gradient of this secant line that goes through PQ, the gradient of the secant line is going to be the rise, which if you look at this distance here, it's delta y, over the run, which is this distance here, which is delta x. So the rise is delta y, run delta x. Okay, so he got that the gradient of the secant line is delta y over delta x. Then remember, in our proof of finding the derivative function, we take the limit as the run here goes to 0. Okay, we make that delta x as small as possible. So we take delta x going to 0. What happens is q moves as close to p as we like, so the gradient of the secant becomes as close to the gradient of the tangent. Taking the limit as delta x goes to 0, we get that the derivative, which he called dy dx, is the limit as delta x goes to 0 of delta y over delta x. Okay, so his notation involved changing these deltas to d's when we have taken the limit as delta x goes to 0. So the notation of dx and dy represent what we call infinitesimal increments. So infinitesimally small, so infinitely small increments in x and y. So infinitesimals are very small numbers, but not necessarily equal to 0, but very, very close to. Approaching. Limit as x goes to 0, So the notation, just be aware, this is quite important to understand that dy over dx here, dy dx, it's not actually a fraction, even though it looks like a fraction. It's a limit of a fraction, so it's the limit of this fraction as delta x goes to 0. So dy dx is not a fraction, but it's a limit of a fraction. Also, a good way of thinking about this notation is that when we're calculating dy dx, we're applying what we call the operator d dx on a function of y. Okay, so d dx is the operator operating on the function y. Okay, this will be important later on when we do higher derivatives, when you see different notation. But at the moment, this isn't so important, but we'll come back to this idea later on, that you're doing the ddx operator on function y. Alright, now that we've got all that technical jargon away, I'm going to do a few questions just applying this new notation. So if y is equal to this, find dy dx when x is negative 2. So dy dx is the derivative. So if y is that, dy dx, remember the rule, bring down the power, take away 1 from the power. Okay, bring down the power, multiply it, so that'll be 6, take away 1 from the power. And constant terms, so no x is there, so constant term goes away when we differentiate. Now we want to know when x is equal to negative 2. When x is equal to negative 2, my dy dx is equal to, let's sub in negative 2 in brackets. Okay. That's negative 56. Okay, another alternate way of writing this is you can write f dash, and then you can put in the x value in the bracket. So you can write f dash of negative 2 is negative 56. What does that mean? That means the gradient of the tangent when x is negative 2, the gradient of the tangent to the curve there is negative 56. So when x is negative 2, that curve is very, very steeply going downhill. Okay. Next one. So given a is that, find dA dr. So we're differentiating a. This is saying differentiate a with respect to r. That's how we say it. Differentiate a with respect to r. So basically we differentiate just like normal. Pi here is just a constant number, so we just treat it like a normal constant. We're differentiating now, instead of we're differentiating x's, we're differentiating r's here. So we bring down the power of r, so that'll be 4 times 2 is 8, and we minus 1 from the power. So that'll be 8 pi r to the power of 1, or just 8 pi r. Okay, next one. So this is d dx of 10x to the power of 5. That basically, that 10x to the power of 5 is the function that we want to differentiate, okay? They've just put the function that we want to differentiate here, and the ddx's are supplying the derivative. Okay, so d dx of 10x to the power of 5, you just differentiate like normal. So bring down the 5, that'll be 50, x to the power of 4, okay? Find y dash if y is that. So y dash is just the derivative, okay? This is my favorite version. Usually what you do is, if they give you y, you write y dash. If they give you f of x, you write f dash x, okay? So just use what they give you and just put a dash there, okay? But if you got the choice, I always like to just write y dash. It's the quickest to write. Bring down the power, minus 1 from power. Okay, linear term is just the coefficient, which here is negative 1, and the constant term goes away. So y dash is going to be 2x minus 1. All right, let's move on and do another question here. So finding points in a curve's tangent is given by a given gradient m. Okay, so let's just go straight to working on this question. Oh, it's A, B. Let's change it to A, B, C. Okay, so differentiate that. So I'm going to work out f dash of x. Okay, linear term is just the coefficient. This term here, bring down the power, will be negative 8. Because 2 times 4 is 8, minus 1 from power. So x to the power of 1. Okay, so that's part A done. B, find the coordinates of the point on the function. And notice it's a point on the function, so a point has coordinates x, y, okay? So we need an x value and a y value, where the tangent has gradient of negative 6. So if the tangent has gradient negative 6, that's saying f dash of x is equal to negative 6. Gradient of the tangent is equal to negative 6. So what we're going to do for B is I'm going to set f dash x to be negative 6. So I'm going to put negative 6 on the left here. We've got an equation that we can solve. Let's bring the negative 8x over the other side. It'll be positive 8x. Okay, let's add 6. And that'll be 8. Divide by 8. That'll be x equals 1. So when x equals, what have we worked out there? So when x equals 1, the gradient of the tangent will be negative 6. But we're after the coordinates of the point on the original function. So we know the x value of the original function. We need to work out the y value of the original function. Be careful. Don't sub back into f dash. if I want to know the y value of the original function, we sub back into our original function f. So we want to work out f of 1. When x is 1, what's the original function? Okay, so this is my y value I'm working out here. So that's going to be negative 2. So when we're at the point 1, negative 2 on the graph, the gradient of the tangent there is negative 6. So that's what B is saying. C. Find the coordinates of the point there where the tangent is horizontal. Okay, so for a tangent line to be horizontal, what gradient of the tangent would that be? Well, that would be a gradient of tangent of 0. So if the gradient of the tangent is 0, f dash is 0. So I'm going to set the whole of f dash x to be 0. So where's my f dash? There it is. I'm going to sub in f dash is 0. So 0 is equal to 2 minus 8x. Let's bring that over there. Divide by 8, we get x is a quarter. Okay, and then we're going to substitute back into the rule to work out the y value, just like we did in the previous question. So 2 times a quarter minus 4 times a quarter squared. Okay, now let me think, that's a half minus, and that's a quarter, which is 1/4. So therefore, the point that we're after, the x value is a quarter, and the y value is also a quarter. So at a quarter, the tangent is horizontal for this particular function, okay? Actually, a quarter is actually the vertex. If you were to graph this function, it looks something like this. And a quarter is the vertex, and at the vertex it's horizontal. The gradient of the tangent is horizontal. All right, what I'd like you to do, work on 604, questions 1 to 15 all, but skip 2e because it's a bit nasty to expand, but do all the rest of the questions, okay? All right.